Boom. What is a robot? Robots in industry. Probably already went over this. All the different ones we have.
Yeah, that's actually a nice slide. Where'd you get that slide? Did you make it?
Media.
It's a pretty good slide.
I say.
You gonna send me this presentation so I can steal some of the slides?
What's up?
You gonna send me this so I can have
Oh,
some
of
of the
course.
slides?
Yeah, it's actually already uploaded onto the Google Drive, but I'll send it to you as well.
That's fine. So
The components here, talking about the big boy that we're going to be using. Give a little idea of the hardware. The end of arm, kind of talk about how they can use different ones in that. External hardware, so you can actually get to do some stuff. The software, nothing too crazy there. An example of this, Robot Studio stuff. Talk about how it makes targets based off of your own coordinate systems and everything like that. Some past projects. The lab next week. Talk about the movels, the weights, picks up. What they're going to be building. Probably not as challenging as this. Maybe just the gate instead of the basic one. And then why should we invest in robots? 5-minute video in the end, in case I ended way too early.
whose video is that?
It was from Putnam. It was from ABB Robotics.
Did you include the video with your robots with katanas?
Oh, we can always pull up YouTube videos after. I've never seen that one.
Video of the two robots dancing.
No, but like.
There must be one.
There's definitely more than one on the entire video.
Oh yeah, look at that. Oh, those look like simulations.
Put it up on the screen.
I'll tell you one up. People program these, you think? That's how you get people to come.
This person needed harder homework.
It's got a lot of views, actually. 360.
It's not that many.
It's more than I got. What's the two robots sword dancing?
Yeah.
It's gonna come up with something weird.
Definitely, yeah.
Do they hit each other? Oh, that's not really fighting.
Yeah. They're still cool though.
Kind of looks weird.
It'd be cooler if they were both holding plasma torches.
Yeah.
Let's look for that next.
All right. I'll have to find some cooler ones for people in the future. Ooh.
All right, so we'll go ahead and get started. I apologize for ending early on Monday. When I got home and used the thermometer, I had 102 fever. And I did suddenly in the middle of class said, I don't really remember why I'm standing here, so maybe it's time to end. So I hope the first half of Monday was pretty good. We're going to continue that topic today, and next week in lab, you're going to get a chance to use the ABB robot that's in there, and Ryan and Adam will help you with that. And so I asked Ryan to talk today. He'll do a very brief overview of robots, but we talked about that twice already, so I think we're good there.
Yeah.
And then go into the breakdown of this robot and how you're going to use it and things you need to know before you get to the lab.
All right.
I'll leave it to Ryan.
Sounds good. All right. So yeah, next week, robot lab, a little more enjoyable than API work, unless you really enjoy coding that much. But unfortunately, you'll still be doing some coding it's in the rapid language that we'll get to. So yeah, my first 4 slides kind of talked about what a robot was, get a little philosophical, break that down, then show different kind of types of robots, the advantages. But if you've already kind of gone over that, then we don't really get into it. Robots are just something that you typically perform a task that you can reprogram. They're reprogrammable, not controlled by an external user. As you can see here, there's a little bit of an image. On the left, it's a crane, and on the right, it's kind of an automated crane. Typical, similar machines, but one of them's automated, one of them's a robot, one of them's not. Because of course your picker upper is getting controlled by a human. Robots in industry, advantages over disadvantages. high productivity. You know, they don't get bored, so they're going to keep working as long as you need them to work. They're continuous, so they keep working no matter how boring or repetitive the task is. They're very consistent. You know, going to have a better resolution than a human would have when they're working on something like that. They're more flexible. You can reprogram them to do different things. They're not only held down to that one task. They reduce the waste because they're not wasting material that a human would. Disadvantages, inability to respond in emergencies. Something like the user hitting the e-stop button on a CNC machine when it goes wrong. They're still limited in some of their capabilities. You know, they're not as dexterous as they always are. Sensors and intelligence is still there. High cost is always a problem for people. Nowadays, there's a wide range of robots performing, more complex tasks, so you can kind of reduce your complexity down and get a robot that's going to cost you less. And then, of course, the big one is that social problem, the moral problem of should we have robots take over the jobs of humans, and that kind of stuff, which we are still kind of talking about today. And then, we have a bunch of different robots. Up here in the corner, you can see you got your kind of linear robots. These are kind of like your CNC machines. You have your X, Y motion and maybe an up, down to Z. These ones are good because, they're very, really cheap in the grand scheme of things, a lot cheaper than the ABB 6-axis robot would be. They can typically carry a lot more weights because, they're a lot more support. You can think about the ABB when you fully extend its arm. Each rotor has had to, have a certain torque and a certain limit to actually, raise that weight up there. So the linears have their advantages. Then you got, your cylindrical and spherical. Once again, a lot of pick and place, not doing too much crazy things. Doesn't really have a big work envelope. Then you got your parallel. Once again, a small work envelope. Not really going to be doing, large pick and place over a large area, but they've been used for something like, the printed circuit boards, picking and placing those in a small work envelope with high resolution, as well as, and sometimes, high speed milling and different operations like that. And then, we have our SCARA robots and then our articulated robots. The one that we're going to focus on is the articulated robot, or the 6-axis ABB that we have downstairs. And, it has a lot of different components and things like that. Of course, you have your different joints in your arms. Each, arm is controlled by the joints. For us, we have 6 joints, but they have, the 7, and then they have them down to 3. The end effectors are the grippers. We have different tools here. We don't really go too crazy in the end effectors. We don't really have any spot welders or things like that. But we have, a bunch of different tools that allow you to pick and place, and some other, in-depth stuff. Then there's the end of arm tooling, something like, maybe once again, one of those spot welders or something like that can be attached to the end of your robot. And, robots are just controlled by the motors, the actuators at each joint, the sensors that can be hooked up to it that we'll talk about a little bit. And then, the big control panel there that, houses the software and the programs that run the robot, that does all the inverse kinematics and kinematics for you, so you don't got to do that every time you, move the robot around. So yeah, so the robot that we actually have downstairs is kind of shown here. This is a little bit of a mock-up in the Robot Studio software that we have downstairs, but this is the actual robot that we run with. It's a 6-axis, as I said. You got your base axis, your 2 arms, your arm, your shoulder, kind of a wrist axis right here, a 5-axis that can kind of go up and down like once again like your wrist, and then the 6-axis that can rotate this end of arm tooling. And they all have different degrees of freedom. You can find that in the literature. And you just want to make sure you know exactly where that work envelope can be. The reach of it, is 1.45 meters. That's just because of the robot that we have. It's controlled over here with a big controller, as I said, that houses the program or the software that runs the robot. And then you have this little device here that's called the flex pendant. That's what we use for control by an operator. The user can actually come in, handle jog the robot around, either with individual joint access or with a linear move or something like that. As well as, you can actually program the robot to remember those moves on the flex pendant. So, you can actually be there with the robot while you're kind of programming it into the moves it has to do. And actually, that's what we're going to be doing in lab come next week, really focusing on how to code with that flex pendant. So right here, this is kind of all the end of arm tooling that we have available to us, even though this is only a small amount that you'd see in the industry. These are really, once again, for pick and place. And they're all controlled by pneumatic actuator or pneumatic solenoid that we have on the robot. We have the parallel grippers, the angular grippers, so radial, and then a suction cup that's run off of a Venturi nozzle. Once again, these aren't going to be your, the ones that you're going to see in industry too often, but we do have the CAD models to, make up the base plates, and, some past projects have actually made, more in-depth end of arm tooling that can do different things, write, erase, glue objects together, kind of, a mock way of welding stuff together. And then, to actually have the robot, act a little more intelligently, you can actually, hook up a bunch of different external hardware. You have cameras, force sensors, limit switches, things like that, that allow the robot to actually interact with its workspace. In the past, we've seen groups, have the visual system pick out different, color blocks and move them to different bins, different shapes, and it can get, more complex as you go. Typically, you're going to communicate with the robot when you're doing something like that through an I/O line, directly connected to the robot, with the PLCs, which is something that will run, I think, in 2 weeks, and then through a TCP/IP connection, which is just one that's made over an internet connection, where basically the ABB will work as a client, and then your camera will work as a a server or something like that, or vice versa, and they talk to each other. We won't really be working with any of these during the labs, but it's nice to know that you can actually hook these up to our robot. And we have a couple different types of software that we use. Robot Studio, which we might just kind of brush upon when we go into the lab. Robot Studio is nice because it allows you to kind of, in a graphical user interface, select different points, different geometries, kind of, simulate almost the real world environment, but in the program itself. And it's just a lot easier than you handle jogging the robot around trying to pick up different blocks. That can get kind of tedious, repetitive, and annoying. So in Robot Studio, you can do a lot quicker and simulate a lot of different, a bunch of different paths that you might not be able to do in real time. The Robot Studio itself generates a rapid code that's used by ABB and other robots. The rapid code is a high-level language, and we'll actually show some examples of it after. It's really nothing too bad. And you can also have other codes that would talk to the robot as well. Python, LabVIEW, MATLAB. We've had groups use Python with OpenCV to capture an image of a certain picture, and then have the robot draw that by making the paths for it. So you can get pretty complex with these softwares. But here we have a little bit of the Robot Studio platform with a rapid code example. If it looks a little foreign, it really isn't too bad. Up here with all the constant and robot targets, those are all basically just points in space specified off of a certain work object. It looks like these ones were just specified off the base, which is the kind of the default work object for the robot, which is located at the base of the robot. You can also, set them off of the tool end of arm tooling. That gives you a little more precision. Or you can make your own work object off in space, which is, nice because you don't have to know exactly where, your base plate or your palletizing work area is in relationship to the robot. You can set it every time. Just makes it a little bit easier when you're going to be doing production style that changes over time. And down below, you can kind of see here, you have the different moves. Kind of a little hard to see here, but basically these moves just say, all right, let's move the robot from wherever you are right now to that next point that's given up above. We have move L's, move J's, move C's. We'll talk about those a little more in depth. I'll show you examples when in the lab. But kind of how it works is, move L's is just a linear move. It's the robot joints working together. The robot kind of calculates out that, kinematic matrix for it, and it's the robot moving with all the joints together, keeping, either the end of arm tooling or its own local axis on the single axis line. Move J's will move one joint at a time, which is good, to reposition the robot after big moves to make sure, you're not running into any singularities or things like that. And then move C's are more of a circular move, something that we're actually not going to work into this lab. And then down below we have, these set DOs, which would just be a command that kind of allows you to, kind of talk to the robot. This set DO, opens up the solenoid or closes the solenoid, kind of allows the gripper to be open or closed. But you can also set those, talk to different, external devices as well. But once again, we won't be doing anything too complicated in the lab. So yeah, just some examples of past projects. We do have a course that I think some of you guys have taken that is Emmy 4815. kind of a split between, advanced robotics and, industrial robotics. You learn a bunch about kinematics, and then you get to play around with the Robot Studio platform and the Rapid Code. This one right here was a group that kind of, had Robot Studio, have a string imported into it with random letters or, a word or anything like that. It would break down that string into, its constituent letters or its elements. And then the robot would be able to, decide what letter it was, where to go grab the stamp from the little work object they have here in the corner, and then they come over here to the piece of paper and stamp it off. This one was pretty good. Not as much robotics as it was industrial. You can see they kind of designed their own end-of-arm tooling, which is something that most robotics students weren't really, doing. They're doing more of the programming side. But it still worked out well in the end, and it was a great little program. Then we can see here's one that's a little more in depth. This one was a robotics major group that kind of had an idea in mind before they came here. They wanted the robot to play tic tac toe against the user, and they used a pixie cam that you can kind of see down here below that would register where the blocks were already, and determine the best spot to put it. They had some algorithm that they got offline. I'm pretty sure it was from a comic strip they got it offline, but it worked pretty well. I mean, tic tac toe isn't too crazy, but still pretty cool to see kind of the machine learning kind of algorithm behind it. And it worked very well. Yeah, so that's kind of an example of how they got a little more in depth. They had a pixie cam that was attached to our Arduino board that would take commands from whatever the user did, push it through the Python code with a little, and push it back through into the robot, and then the robot would know exactly where to go, in space, depending on what move the actual player made. And it would also kind of have different poses if it tied, if it won, or if it lost, just to add that, little extra bit to the end. And then I think one of the coolest ones that we've had was a group that actually kind of imported a picture or something like that. As you can see here, it's a little picture of a skyline. They would import it into MATLAB. MATLAB would kind of do some image processing using their libraries to find the edges and the curves and things like that. It would then generate a text file. That text file would then be sent to Robot Studio, or in Robot Studio they would generate the rapid code that would tell the robot exactly where to go when they're drawing. And then depending on how great the marker they're using and how great the text file was, you can see that they got various resolution out of there. This one is a little messy. Kind of had a hard time catching some of the sides, but you can see here that the Taj Mahal came out a lot nicer. And this was doing something real time, so the robot was given the image. It was generated in a minute or two, and then it was outloaded to ABB. So it wasn't like this is something they spent a whole month trying to get one image. This is a new image every single time, so it was pretty nice to see them do that. But for our lab, we're going to kind of go back and just kind of go to the basics. So for our lab, we're going to kind of do what we call the online robot programming. You can either program the robot online, which means you're actually there with the physical robot with the flex pendant, moving the robot to a certain location, telling the robot, hey, I need you to pick up this block, and then moving to the next location, dropping it off, and continue doing that until you have the whole path set up. There is also the offline programming, which is all done in the ABB or the Robot Studio software. And we might show you just a little bit of that just to get an idea of why it's a little bit easier for you. But the ultimate goal is to kind of stack these blocks together in either the basic or challenging way. We've kind of found that most people try to go for the basic one and usually only get to the first level because even the basic one's kind of hard. The robot itself kind of has a little bit of a lag to it, so when you actually do try to jog it around, it might move a little bit quicker than you think it will, and you might move it right into the the bottom of the block that you've already placed. But if we will kind of want to just kind of walk through how we go for there, when you come into lab, you're going to have this little base plate set down with a bunch of identical blocks all set up. The robot's just going to be out there in space, and the flex pendant itself is going to be open to a new module. This one already has some code in it, but when you come in here, you're only going to see procedure main and end procedure. In there, you're going to make your own code. From here, we can kind of see that you have a bunch of moves, some weights. Once again, move L is for that linear move. And what it's telling is basically move to point 10, V is giving your velocity. This is a move to point 10 with a velocity of 1,000 millimeters a second. I'm pretty sure where we're in. Unfortunately, you're not going to be able to go 1,000. It's going to be a lot less, probably around 250. We're capped out at just because it's more of a learning tool and we don't want to hurt anybody. And then it's basically saying, all right, you don't need to move here exactly. You can move there, at least get in as close as you can with the radius of something like 50 millimeters. And you're based off of your tool that you already have out there. This move, would make one move, and as long as there's no errors that came up, so, singularities that you can run into, or, big joint movements, then you'd move to that point, and then the robot would look to the next point and continue on, picking up the blocks as you go. And yeah, we'll actually go into more detail with that when we actually have you there with the robots. We could actually show you the moves when the robot makes them. And we have a bigger lab module on Canvas that you can take a look at that kind of walks through the different moves, as well as, just gives you some information on the robot that wasn't covered here. Does anybody have any questions about the lab? I know most people here I've seen actually use the lab, so that's going to be pretty good. Or any questions on robots at all, if I can answer any of that. If not, I guess I got a little video at the end. A lot shorter than I really expected, but this is just a video of why we should, use robots and what are the advantages and everything like that. Yeah. Do you think of anything else to add?
Too bad we don't have like a spare parts package or something to bring in and show them, I guess. That might be useful if they know what they're looking at before they show up.
I actually didn't watch this beforehand.
Oh, you don't mind sign up for robot time. We should just project team a while ago. That's a very low power cycle on it.
Very low power. It's a plastic cutting. Or a foam cutting actually. Those are weird shots. Those are weird shots at the end.
For your free guide, go to that website. Figure it out. Go to that website. Oh, this will be cool because somebody else can run the computer while I talk. What'd you think of the 10 reasons? We've talked about some of that stuff in class already. Did you agree with all 10 reasons? Was any of them that stood out when they went by in that video? Can anybody name one of the 10 reasons, or did you all sort of zone out when the movie started? Right, they talked, they use like dusty hazardous or something like that, but are dull, dirty, dangerous. And so I think absolutely 100% that's a good reason to automate, good reason to use a robot. Everybody agree with that? So, did you find the website? Or otherwise we can frame by frame through the movie. I want to talk about the 10 reasons. All right, go back to, give me number one, put it on the screen. 10 good reasons, yeah. So they said 10 good reasons to invest. So who's their target? Their target is somebody that's going to buy a robot. So some manufacturing company is going to invest in capital equipment. So reduce operating costs. So if my target is somebody that's, yeah, I'm pretty sure that's the first thing I'm going to tell them. So reduce operating costs is what they got first. Make the screen go up. So people don't erase. Now I have to move the table that I wanted to sit on. Okay, we want operating costs to go down. What's number two? Quick. Number two, improve product quality and consistency. Okay, number three. Improve quality of work for employees. So improve the employee experience. Yep, next. You see the pattern, right? As soon as I start writing, I know what it is. Increase production output rates. Okay. Increase flexibility. Reduce waste. Comply with safety. Reduce labor turnover and difficulty of recruiting workers. All right, is that all of them? Did I miss any? All right, you can make the video go away. All right, so we operating costs down, increase production rate. So operating costs down, that's how they were doing that, right? And this one, maybe not. So when do you want to increase the production rate? We talked about this in general with automation, right? When there's a customer that wants to buy faster, right? If you don't have a customer that wants to buy faster, then you don't necessarily want to increase the production rate unless it frees you up to go make something else that the customer wants to buy. So that probably doesn't reduce costs, that probably increases profit. But why does anybody want to reduce cost? To increase profit, right? I do not care what the cost is if the profit's high enough. Right, so the only reason we care about reducing costs is to increase profit. Reduce waste. They must have a really good argument for how it reduces capital costs because it requires a capital investment, right? So how do you guys think, if you were ABB, how would you argue that it reduces capital cost? What do you think? Yeah, employees are not capital. That's the problem. It's operating expense. So I could see reduce operating cost. Do they say that somewhere? They increase production, reduce waste, save space. Oh, the total at the top, yeah. So if you had to say it saves capital, how does it save capital? I think I know how they justify it. Anybody have an idea? Well, I'm pretty sure it's because of this. If I can increase my production rate, then I don't have to buy another machine to make the same volume of parts. And so when you're looking at, I've got to make, I had an example of a part run. They needed 300 pieces. So they need 300 parts, 7.5 hour tack time. How long does it take to make 300 parts? Well, you make 21 parts in a week, 24 hours in a day, 7 days in a week, right? And so to fill that order, that shop ran 24 hours a day, 7 days a week. So increased production rate. So I think that's how they justify reducing capital cost. Do robots improve quality?
I would say not necessarily. I think the consistency part of that was the key. Like they are, I would say, more consistent people, but quality.
They tend to be extremely repeatable.
Right.
So if you screw it up, you'll screw it up the same way every time.
Exactly.
And I think there's that. In certain situations, some robots may have more precision than a human operator would have. When you need that precision, then they may increase the quality. But what really makes improved quality isn't the robot. What makes improved quality is the right process. And so, and this is, I think Bill Gates is famous for this quote, is that if you have a crappy process and you automate it, now you can do your crappy process faster, right? So you have to have a good process before you try to automate that. So I'm not, I mean, yeah, we like to make that argument, but I'm not even sure that that one is valid across the board. They help you comply with OSHA rules, right? Yeah. Unless you screw up with your guarding on your robot, in which case they can help you violate OSHA rules. But yeah, that makes sense. Improve employee experience. How did they word it? That's not, I paraphrased. But they meant make the employees feel warm and fuzzy, right? You've heard about the factory of the future. Like 2 employees, the guard and the dog. Guard's job is to feed the dog. Dog's job is to make sure the guard doesn't touch the damn machines, right? The factory of the future. So I think that this one is absolutely not automatic. But if the company is smart, they use the ability to do it because you can. And if you're smart, you'll make the employees embrace the robots instead of fear them. I'm not sure that it reduces the turnover, but that wasn't the whole thing that they wrote there, right? They also talked about the fact that it's going to be hard to recruit people, or it's hard to recruit people into those jobs. So a few years ago, there was a study that came out that said at that moment, and so this was probably like 8 years ago now, the study came out. It's very famous, people quote it all over. They said at that moment in the United States, there were 600,000 unfilled jobs in manufacturing, which they could not fill the position because they couldn't hire a skilled worker. And that was like 8 years ago. As the baby boomers retire, that problem gets worse. They're projecting in a couple years it'll be at 3 million unfilled jobs that they can't find a skilled worker to go do the job. And that's the problem that they're insisting that robots have to be able to solve. If you, so just think about that. We talked about this earlier in the class though, right? But there's something like 250,000 manufacturing companies in the United States. 4,000 of them are bigger than 500 employees. Most of the rest of them, 75% of the rest of them are fewer than 20 employees. So let's think about that when the 20-person facility has someone retire and they can't replace that person. That was 1/20th, so that's what, 5% of their workforce gone. Now the amount of work that they're doing is actually not decreasing. The amount of work available for those companies is increasing right now. So as the workforce dies, so those companies, in order to survive, have got to figure out how to use robots. That make sense? What else do we got? Oh, increased flexibility. I wrote it over there because I was trying to find things that fell under operating costs. And maybe this ties in over here with the reduced capital. Again, we don't have to buy a different machine if this machine can do 2 different things. So I think, I don't know, I was skeptical with their 10-point video when it flashed up on the screen and I was watching the things go by. But do we agree? This is probably true? Okay. Let's talk about the rest of the term then. We've got a few minutes left. Anybody know where I put the cap for the whiteboard marker? Thank you. Eagle eye. Oh, we should have done nicknames for the class. Everybody could have had a nickname. I had a class years ago. Maybe you guys were in it. Emmy 1800. Several years ago, there was a kid in the class that his nickname was Heroin Kid. No? There was a good story behind that one. It didn't involve ingestion or use of heroin. It involved discussion of heroin. But, oh, that same guy on his first day at lab didn't have shoes. And I said, you can't come in without shoes. And he says, but I don't own any shoes. He had sandals. And I said, well, you better go buy some. And he came back about 10 minutes later with shoes on. And I said, you found some? He says, they're my roommates. So the rest of the term, we have no school Monday, right? Patriots Day. Could be patriotic. Anybody running? No. Anybody watching? You watch a marathon? You're gonna go to watch, or watch on TV? Yeah. Drink beer, watch it on TV. Yeah. Sounds like a plan. You're probably not old enough to drink beer in public, so. No, don't make me laugh. Don't make me make myself laugh. I always think my jokes are funny. So then we got Thursday next week. We got a Monday, a Thursday, and a Monday. Is that correct? Okay. And we've got Robot Lab next week, PLC Lab the following week. On Thursday next week, we're going to begin the discussion of PLCs, programmable logic controllers. And I was going to make these guys memorize it and lecture it to you, but instead I'm going to provide you with a video that you can watch. And maybe I'll make these guys come play the video in class and take attendance now. But I will, I've done that lecture about a dozen times. And so right now I'm picking through the videos of the dozen times when I've done that lecture. And I'm editing together the best version of it for you guys to have for introduction to PLCs and programmable logic controllers. We'll continue that discussion on the following Monday, and all week that week you'll be working on the PLC lab. You've also got your API programming lab, which is due at the end of the term, right? And I'm thinking of that sort of final, bring it all together, kind of cumulative discussion / evaluation. Because I remember I told you the last time I taught the class, it was a smaller group, about this size, actually. If only you guys wanted to get a grade for the class, it would be perfect. What we would do is we would have an oral final exam, and we would just sit down and have a discussion and make sure everybody understood something. Since I know that the people watching from home, or not watching from home, also probably want a grade. And if I announced that we were going to do that, then all 40 people would show up on that last day, and I wouldn't recognize half the faces. What we're going to do is, I still want to get some of that feel into it. And so what we're going to do is I'll give you a take-home final exam that involves stuff that we've talked about in lecture and involves stuff that you've learned in the labs and gone through in the labs. And will involve a question which allows you to suggest questions for an oral final exam. So this is, you need to create a question that you would ask somebody else in the class to help you evaluate whether they learned anything in the class. Okay, so not a question that you want to be asked, one that you want to use to evaluate somebody else. Okay, and then on that, we could do it on the Tuesday, right? We have a lab scheduled on the Tuesday. Right, is that, no, it would be more fun if that was like at 3 to 5 in the afternoon. Make you guys come for the last 2 hours of the term. We'll do it on the, try to, I'm going to make that take home also. I figured it out. The question that you ask, so think of a question quickly.
Why automate?
Why automate? All right. So the answer to the exam question is going to be for you to make a video that says why automate. And then the answer to the oral question is I'm going to distribute those questions around to the other people in the class, and they can make a video of their answer. And that way everybody gets to participate. And we'll judge, I want to have a feeling for everybody. So rather than, because I was thinking take Thursday and Monday, and have half the class come to each one, but I'd rather have more time to talk on Thursday and Monday. So that's how we're going to do it. Or we could just tell everybody that's not here today that they fail and that only these people get to participate in the oral exam. That would only work if I said that that's how it was going to be at the beginning of the term, I think. So, all right. And since I only had to talk for half the time, I made it through the whole class. So thank you guys for being here. I will see you. I will see you again, I don't know, in like 3 weeks.
Remember, teams not signed up for 2 hours on the robot, do that, because it does the robotics QPs are also going to want to sign up for time on the robot. You get that done